In this video, we're going to cover numerical integration. So essentially, numerical integration is how we approximate integrals that we might not necessarily be able to exactly integrate. So in Calc 2, up until this point, we've been focused on how can we integrate things? What functions can we integrate? Here are strategies for integrating. That does not mean that every integral that one encounters can be integrated using those methods. So numerical integration enters, especially for functions that cannot be integrated for some reason. That doesn't mean that the area under the curve can't be approximated. We can still approximate the integrals even if they're not exactly known. So we're going to cover the approximation techniques. So the first technique for approximating is called the midpoint rule. So for the midpoint rule, we have a picture here to illustrate what's happening. We're familiar with finding the area under the curve. You may have even seen the midpoint rule before. You may have learned left-hand rule, right-hand rule, midpoint rule. So midpoint rule is the most comfortable. What do you do for the midpoint rule? You take your interval that you're integrating from A to B, and you split it up into a certain number of what we partition the interval into a certain number of subintervals, and each of those subintervals have a same length as each other. So in this case, we have 4 subintervals, 1, 2, 3, 4, and our delta x, the width of each of these rectangles, is the same on every single interval. So that's important to note, our delta x constant. Okay, some people call the delta x the mesh. And they would say that we partitioned the interval A to B and we have a mesh of delta x. So we already know how we make the midpoint rule more or less accurate, right? We have more subintervals for more accuracy. Delta x goes to 0, and that's how our approximation becomes an exact integral. But in this chapter, we're focusing specifically on just approximating. So we're not going to do that limiting process. We're just going to stick to the rectangles, right? So with the midpoint rule, as you would suspect, the height of each of our rectangles is the midpoint. So we're going to call those m's, m1, m2, m3, m4, and that'll approximate it for us. So in general, what is the midpoint rule? The midpoint rule is we're going to add up the area, adding up the area, and we're going to range from I equals 0 to n, where we're adding up the area, so we need a width times a height, right? So it's going to be f of x sub, well, we should not use x, we've called them m's, right? So f of m sub I times delta x, where m sub I is the midpoint of the ith sub interval. Okay, so this is height times width of a rectangle. Pretty straightforward. And then the the sigma notation means just add them up. So I think we've seen midpoint rule quite a bit, but let's just make sure, we're feeling comfortable with it. So could we draw this with rectangles? Yes, we could. If you are interested in doing that, you can go ahead and do that, but let's just focus in this video on using the formulas to kind of expedite the process. In practice, you would probably be programming a computer to do this for you. If you are comfortable using something like Excel to do that, that's one program that most students have, and that's completely fine. You can use Excel to do that. How would we do that though? We would use our sigma notation, right? So first we have to find we would find a general formula for the midpoint and program that. It's a little more complicated. We're just going to do like a simple example of 4 subintervals. So I recommend doing this particular one by hand. Okay, so let's find our partition here. So from 0 to 1, we're going to cut it in half, and we're going to cut each of those in half. So this is going to be a quarter, a half, 3/4 and 1, and just verifying that we would have 4 rectangles here. We do. Okay, so now we need the midpoints. Let's find the midpoints. Okay, so the midpoints would be 1/2 of 1/4 is 1/8, and then halfway between 1/4 and 1/2 we would have 3/8, and then halfway between 1/2 and 3/4 we'd have 5/8, and then halfway between 3/4 and 1 we would have 7/8. Okay, so to add this up, we would then need to compute what is our delta x. Delta x is consistently 1/4 because we have 4 subintervals. Okay, so then plugging into our formula, we would have f of 1/8 I'm going to actually pull the, well, not yet, getting ahead of myself. So f of 1/8 times 1/4 plus f of 3/8 times 1/4 plus f of 5/8 times 1/4 plus f of 7/8 times 1/4. Okay, so notice how the delta x is in every single term. Why not factor that out, right? So we can just factor out our 1/4 times f of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. Okay, so this is where we can use our technology to kind of expedite just the arithmetic process of this. If we jump over to Excel, let's go ahead and set our cell to be equal to x squared. Okay, and instead of making it x squared, let's make it the cell to the left. So this is going to be the cell to the left squared. Okay, so equals that squared, and then we'll plug in, this is a 1/8. Programming that as a date, that's interesting. Number. Okay, so there we go. Now we have 1/8, we have 3/8, we have, we'll fix the settings in a second, 5/8 and 7/8. And for all of these, we'll format the cells to be numbers. Three-eighths, 5/8. And 7/8. And then we'll drag down the formula. Okay, so then we can add those up. This is equal to the sum of F7 to F10. There we go. And then multiplying that by 1/4. There we go. It's equal to 0.328125. So roughly, I would say about a third. We got about a third, right? Pretty close to a third. And we should not use equals there because it was clear that Excel was rounding that, right? Okay, so just kind of once again, Excel is one tool that you can use to do this. I kind of like using Excel just because I'm familiar with it. Maybe nowadays there's something a lot more modern, not to date myself, but it's been a while since I was learning about this for the first time. So maybe there's been some cool technology that's come out to make this a little bit faster, but Excel is kind of what I think is helpful to help out. Okay, so that was the midpoint rule. And we're expecting this to not be very accurate, right? So why would I expect this to not be very accurate? We only had 4 intervals. So if you went ahead and computed what the integral actually is, for this integral, like we could easily compute it. The exact value for this I already worked out. And compared to the exact value, we would get 1 over 192, which is equal to, well, roughly equal to 0.0052. Okay, so big, I would say relatively big error. Why? Not very many intervals. Okay, we only had 4 subintervals, so we were kind of expecting that, right? Okay, let's take a look at another way of approximating. So obviously, giving more intervals, more subintervals is going to be a way to get more accuracy, but there's also there's other ways to approximate these. So let's do some ones we maybe haven't seen before. There's a rule called the trapezoidal rule, and I think it kind of gives it away. What if we used the same concept of breaking up our interval into subintervals, but instead of looking at rectangles, let's use trapezoids because they look better. They look closer, if that makes sense, when we're looking at the visual picture. So here's the same curve as we saw with the midpoint rule, but we've broken our interval up into 4 subintervals, and instead of doing rectangles, we did trapezoids. So there's 1 trapezoid, 2, 3, 4. Okay, and recall that to find the area of a trapezoid, what we did is you average the bases, base 1 plus base 2 over 2. That's the average, and then you times by the height. So this is where this formula is basically going to come from, but we'll simplify it so that it's a little bit more usable. So what the trapezoid rule ends up being when we apply this area formula is we end up getting 1/2 times the delta x times, okay, so that's coming from the over 2, adding up the bases and multiplying by the height. The delta x here is functioning as the height, so we've got h over 2 out front, and then when we do the work of adding up the bases and averaging, it simplifies down to f of x0 plus f of x sub 1, f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 of f of x sub 3, so on and so forth. But then the last one, f of x sub n, does not have a 2. So you'll notice there's a 2 coefficient on every term except for the first point of our partition and the last point of our partition, because when you average, it's going to be included on 2 trapezoids except for the start and the end. That's the base on just one trapezoid. So that's why those 2s are popping up there. Okay, so that is our trapezoid rule. Let's go ahead and use it. And this time we're going to estimate an integral that we could not estimate, like we could not exactly integrate. So if you look at the integral from 0 to 1 of e to the power of x squared, we're going to do 4 subintervals. But if you tried to compute the exact value of this integral using our by hand techniques, it's not going to work. So basically, even a very intelligent computer that is using algebraic solution methods would choke on this because it cannot be done. However, calculators, computers, and the like often know both methods. The smart ones will know algebraic as well as numerical methods, and they'll just default to numerical. So when you tell your calculator to do this, it's going to do what we're doing, basically. It's going to do it better than what we're going to do here using only 4 subintervals and the trapezoid rule. It's going to do something a little bit more advanced because it'll basically do it with more accuracy than 4 subintervals. But we need a little bit more calculus to really explore what it is doing behind the scenes. So we'll just leave that as a question to be answered in the future. Okay, so let's do it. We're going to estimate this 4 subintervals. So let's break 0 to 1 up. Okay, we've got 0, 1, the 4 subintervals, a half, a quarter, 3/4, and this time we don't need the midpoints because we don't need that for our formula. So just looking at our trapezoid rule, we need to fill in the fact that we have a half times the delta x, which is a quarter, times f of 0 plus 2f of a quarter plus 2f of 1/2 plus 2f of 3/4, right? And then last term, sorry, plus f of 1. Okay. So now, let's go to our Excel. And let's break out. Let's do a column of numbers again. This time I'm going to format them as numbers first. Yes. Okay, so we're going to do this for 0, a quarter, a half, 3/4, 1, and then we have, for our formula, equals EXP is, I believe how you have to enter it. So you see when you're in Excel, it'll explain like what each function is. That's nice. Okay, so EXP, I did not enter the number yet, but it's going to be the exponent of this, our cell to the left, and then we need to square it. Sorry for the fumbling. Clearly the coordination's not here right now. There we go. That's what we were expecting. Okay. Okay, just checking our formulas. Yes. Okay, looks good. So this is computing our f of x column. Let's maybe label it just for reference. This is computing our f of x. This is our x values. And then we need to add up. This cell will be our formula. This one's going to be equal to, okay, a half times a quarter. So that's an eighth. 1/8 coming from our formula. So that is the 1/2 times the delta x. built in already, since we've already kind of done that work on our paper. Now we're going to multiply by the following in parentheses. So we've got first one plus 2 times the second one. Two times this one. You have to use the asterisk to do multiplication, which I constantly forget in Excel. Plus 2 times the fourth one plus the last one. Okay, so just making sure our formula is good. We've got an eighth times the first one plus 2 times the second plus 2 times the third, 2 times the fourth, and the last one. And there we go. We get 3.26. 3.26 for our trapezoid rule on this one. Okay, there we go. Looks good, right? So we don't have the exact integral to compare it against, but you could try out if you're comfortable using, if you tend to use your graphing calculator a lot for this, you could test out what your graphing calculator says and just give a point of reference. So this particular example especially really begs the question, how do you know how accurate you are if you can't compute the exact value? Which is a really good question, right? When we're approximating, you always want to know how good your approximate is. And there are actually ways to tell how good the approximate is. We're going to cover one more technique before we actually get into finding the bounds on the error, like basically getting a handle on how far off these approximates are. But the one last rule for approximating that we're going to cover is called Simpson's rule. So how we will visualize this is just kind of by imagine that instead of using a trapezoid, we used a parabola and we integrated under the parabola on each interval. So here is an example where we have 2 subintervals. The first picture is 2 subintervals. Okay, and our P of X here is determined by a parabola that goes through uniquely determined by 3 points. Okay, so then if we went and took our same interval and we broke it up into 1, 2, 3, 4 subintervals, then that creates 2 parabolas because it takes 3 points to uniquely determine a parabola. So the reason these are color-coded here is because this is one parabola and it took 3 points to uniquely determine it. You cannot determine a parabola with 2 points, so you have to involve other points in your partition. So 4 subintervals gives 2 parabolas. Okay, so the formula for Simpson's rule here is where this comes from. Okay, so for Simpson's rule, it's gonna come from adding up the process of integrating a parabola. So remember when we integrate like x squared, we end up getting a third x cubed. Kind of hold that in your mind for where this is coming from. Deriving this is actually fairly complicated and it's beyond what I would like to explain in this video. So you'll kind of take my word that these numbers are coming from the process of integrating parabolas in general. So here's Simpson's rule. We get a third times delta x times f of x sub 0 plus f of x sub 1 plus f of, okay, so it's f of x sub 0 plus 4 times f of x sub 1 plus 2f of x sub 2 plus 4f of x sub 3 plus 2f of, and just continue on. You continue on alternating. So the pattern is two times the third to last one, 4 times the second to last one. So it goes 2, 4, 2, 4, 2, 4, 2, 4, clear until you get to the end, and then you get to finish with f of x sub n. Okay, so the pattern goes first and last, no coefficient, and then on the terms it alternates between 4 and 2. And this is giving you the area under those parabolas that we're approximating. Okay. For those people that are curious, there is a very nice proof of this in the OpenStax Calc volume 2. And you can see the full proof and explanation of where this came from on page 323 and 324. Okay. So again, this is fully optional. If you're just very interested and you want to see it, that is where you can go to take a look. Let's dive into using, to answering that question that we started posing earlier, which is how far off are we? So how far off are we can be more accurately described as finding a bound on the error. So let's make sure that we're comfortable with some basic terminology first. You might hear people refer to something called absolute error. So let's say you estimate a value with B and A is the exact value. The absolute value is when you take the difference between the exact and the approximate and you take the absolute value. So basically saying like, okay, this is the amount that we're off, and we get rid of the positive versus negative with an absolute value, just saying we're this far off. Relative error is, well, okay, so if your approximate is 1 unit off and you're working with very big numbers like 1 million, being 1 off isn't that bad. But if you are 1 off and you're working with decimal places, so like you're working with numbers like 0.001 and you're a whole unit off, that's a lot, right? That's actually very different. So relative error is when you compare how far off you are with basically the magnitude of numbers that you're working with. So to compute the relative error, you take the difference and you divide by the exact value for what you're looking at. Now, the problem is we don't always know A. I already showed you an example when we did our integral of e to the x squared. We didn't know what A was. We couldn't compute that by integrating. So we're not going to be able to always just say the absolute error is this, the relative error is this. We're never going to be able to do that for those problems that involve things we can't integrate. So this is why we need error bounds. We need to have a way for saying, okay, at worst, it's going to be this far off, at worst. We won't be able to say how far it is off, but we can get a handle on how bad it could be. So here's our assumption for these functions that we're working with in this unit. So our function is continuous. So f of x, whatever we're working with to integrate, needs to be continuous on the interval. Next, the second derivative needs to be well defined. Okay, so that means that the second derivative, you can compute it at all values in that interval. Okay, then we're going to find the maximum value of that second derivative, the absolute value of it. So we're going to find the maximum of how that second derivative, the maximum of that function, the absolute value of it on that interval. Okay, here are our formulas for midpoint and trapezoid rule. Okay, so the error for the midpoint, the error must be less than or equal to that max value, m, times how big is your interval, b minus a cubed, over 24n squared. In other words, this is the piece that handles how many intervals did you do. If you didn't do very many intervals, your error can be pretty big, okay, because you're dividing by a very small number. If you make your n big, you are dividing by a very large number. When you divide by a large number, that makes your actual fraction smaller. So like 1 over 100 is smaller than 1 over 4, right? So this is kind of confirming what we knew, which is you do more intervals, more subintervals in your partition, and you get a more accurate result. Okay, same thing for the error in the trapezoid rule. Okay, you take the maximum times b minus a cubed over 12n squared, where n is your number of subintervals. Okay, and Simpsons. Let's add in Simpsons. So error in Simpsons is going to be less than or equal to m of b minus a to the 5th over n to the 4th. Okay, and this is going to be, let's call this m star. It's going to be a different m. M star in this one is equal to the max value of the absolute value of the 4th derivative. Okay, I almost left this one out, but I want to make sure you have it for your own references in case you end up using Simpsons rule quite a bit in the future. Obviously, Simpsons calculating this error is hard to do by hand. You would have to calculate the 4th derivative, find the max of it. It's a rather tedious process. So we're not going to do too many of those at all, but it might be that, Simpsons rule, despite being a pain, might actually be the most accurate method in the future for you. So those are the error bounds for the 3 approximate techniques that we have found before. Okay, so let's practice calculating the error bound. So let's say we want to know how many intervals we should use to guarantee that our estimate of that integral, e to the x squared from 0 to 1, is accurate within 0.01. So basically, we want to know how to keep our error bound less than that 0.01 value. Okay, so we're going to highlight this. This is going to be our error bound. We're using the midpoint rule, so we're going to keep that in mind. First, let's find our m. We're going to go back to this formula for the midpoint rule. Midpoint rule was less than or equal to m times b minus a cubed over 24 and squared, and we want this to be less than or equal to 0.01, basically, is what we're saying. So we want to make sure that we solve for an n that makes us less we want to solve for n such that we are less than 0.01, if that makes sense. Because our m, we don't get to solve for, like that's just set by the problem. Our b minus a, we don't get to solve for. So in this case, let's fill in what we know. We know that b minus a in this case is 1. We know that we're going to find what m is. Find m, which is equal to the max of the absolute value of the second derivative. Okay, so first we need to calculate the second derivative. F of x is equal to e to the x squared. F prime of x, we got chain rule galore happening here. So first, it's e to the x squared. Chain on the derivative of the inner function x squared. So that's our first derivative. Now we have a product rule that's happening. So I have 2, so taking the derivative of 2x, e to the x squared, plus, now I'm going to take the derivative of e to the x squared, which is, again, 2x e to the x squared. There's my second derivative. So when I simplify that, I get 2e to the x squared times 1 plus 2x squared. And finding the maximum of, this is going to be positive. The absolute value is going to be positive for this function. So we're finding because we're finding the maximum value of things that are already positive or on 0 to 1 already for our interval, that's going to be equal to just the second derivative function on 0 to 1. Okay, so I can drop the absolute value bars. I just need to find the maximum of this function. Okay, so this is where you can do your first derivative rule. This is also where technology can help us. And I think that technology is probably the most intuitive piece. So remember, in Calc 1, you learned the first derivative test for finding max values. So the first derivative test says you have to look at wherever the derivative is 0, and then you also have to look at where you have maximum value, where you have to look at the endpoints as well. So we could take another derivative of this function, or we could use technology to assist us here. And I think we're going to do the technology just to kind of get a feel for how the graph can help us here. Let's take a look. We're going to graph y equals 2e to the x squared times 1 plus 2x squared. Okay, so I'm going to go ahead and take a look at the graph here. You notice how from 0 to 1, it looks like our function is strictly increasing, and it's continuous on that whole interval. I don't see any point where the derivative would actually be 0. So basically, we're going to achieve our maximum value at the endpoint of 1. Okay, so we're using our graph. And using our graph, even though the graph is not necessarily a proof, it is helpful here. Okay, so we found that the maximum value is achieved at 1. I misspelled achieved. I before E. Okay, so the maximum is achieved at x equals 1. 2e to the 1 squared times 1 plus 2 times 1 squared, which is equal to 2e times 1 plus 2 is 3, which is 6e. Okay, so the error, filling that in for m, we have error for our m sub n is going to be less than or equal to 6e times 1 cubed over 24n squared. Okay, so now we solve for the n. That is going to make 6e over 24n squared less than or equal to the desired 0.01. Okay, and this is just algebra, right? So we have, this is always a positive, 24n squared is always going to be positive, so I can cross multiply here. Okay, and we divided by a positive, so again, I'm not going to do anything. I'm going to divide by 24, divide by 24, so 6e over 0.01 times 24. So that will move this will become 6e over, so this will become 600e over 24. If we simplify, 6 over 0.01 is 600. And then taking the square root of both sides. Okay, again, we're working in all positive numbers, so we don't have to worry about some of the algebra rules that surround inequalities here because everything is nice and positive. So I get that n must be bigger than or equal to square root of 600e over 24, which is approximately 8.24. Okay, so n equals 8, not good enough. N equals 9 or larger would result in error bounded by 0.01. Okay, so n, why couldn't I make it 8.24? Exactly, because n is supposed to be the number of subintervals. You can't have 8.24 subintervals. N is strictly an integer, right? So I had to go to the next biggest integer. If I went to the next smallest integer, it doesn't satisfy the inequality, right? So n needs to be bigger than 8.24. Okay, so it's kind of cool. So basically how this is going to work in practice for the people that are going to be engineers, scientists, you will be given a lot of different formulas within whatever projects you're doing. And someone's going to say, okay, well, we have to do it this way in order to get it accurate enough. This is the math that goes into figuring out how in depth you need to go, basically. So there's going to be error bounds for all different types of problems. This is just like one application of an error bound, but the concept of an error bound is going to be all over the place for the sciences because that's kind of like your whole job. So only mathematicians really live in the exact world, and all the scientists and engineers and everyone else is going to basically live in the world of the approximate for most of what they're doing. And this is the end of our numerical integration techniques video, and I will see you next time.